All right, so here we are in section 5.2. We're going to look at sigma notation and limits of finite sums. And for you guys who are watching this later on YouTube, we are doing this here in live lecture today. So you gals that are on the call with me here, if you have any questions while we're going through this, just throw them in the chat or unmute yourself and we'll get that taken care of. Okay, so first thing to look at here is sigma notation. And depending on what your last math class was, maybe how long it's been, you may or may not have seen this in the past. So for some of you, this might be some review. For others, this might be a little bit new or it's been a while. So I just want to make sure we're all on the same page with this notation here. So sigma notation is used for a sum of many terms, and this is what it looks like basically. We've got this big symbol here. It's kind of like an E type of shape. But what this is the Greek letter sigma, which is, I think, the Greek equivalent of like a capital S. And that is our summation symbol, indicating that we're going to take a sum here of some different terms. Okay. And then on the sigma symbol there, we have some different things written around it. We have down at the bottom here something like k equals 1. And, this K here, sometimes you'll see that written with different letters, like maybe I or J. Usually it's one of those three, I, J, or K. This is just called the index down here. And it tells you where we're going to start our summation. Okay, so we're going to start with the value of k equals 1. Okay, and your starting place here can definitely vary. You don't always have to start at 1. Sometimes you might start at 0 or 2, or you can dictate the starting place for your index. It should be some integer though. So k equals 1 is just kind of a common starting spot for our index. And then up on the top of our sigma here, there's going to be some number n. And that could be, sometimes it's just written generically like that as n itself, but often there'll be a number there. And that's where you're going to stop your summation at k equals n. So your index is going to count up like k equals 1 and then 2 and then 3, etc. You're counting up by integers until you get to n, and that tells you where to stop. Okay. And then on the right side of the sigma notation right here is going to be a formula of some sort. And generically, we can just put something like a sub k over there. I'm trying to make it nice and big to match the big sigma here. Okay, a sub k, and that is just a very generic notation for a formula. So this is a formula that's going to give you your terms that are being added up. So formula for terms to add up. Okay, and so each time your index k changes from 1 to 2 to 3, etc., that's going to give you a new term, a sub k, based on whatever k value you're on at the moment. And then you'll just keep adding up those different terms. So something like this, if we just do it very generically, this means we're going to add up a sub 1 plus a sub 2 plus a sub 3, and then you keep going until you get to that stopping index, a sub n. And so that's what the sigma notation tells us. It gives you the formula for these terms, how many terms there's going to be, where to start, where to stop, and then you add all those terms up. Okay, so for a couple quick examples here, problem number 1, we're going to write out the terms and find the sum for these two sigma notations. And we'll just focus on the first one here. This is the summation from k equals 1 to 4 of k cubed. That's our formula right there. So that, by the way, is how you would read one of these. The summation from k equals 1 to 4 of k cubed. Okay. So we look at our starting index. It's the nice generic little k equals 1. And so we're going to start with k equals 1 and write our first term down. And so we're going to take our value of k and cube it. So we got 1 cubed, and that's our first term. And then you kind of mark up your index by 1. What would that be called? Increase your index. Yeah, go up to k equals 2, and your next term is 2 cubed. And then increase again, k equals 3. So you get 3 cubed. And then k equals 4. That would be 4 cubed. And notice how that is actually the ending value for k that's written up on top of the sigma. So we want to stop at k equals 4. So you don't keep going after that. You just, these are the 4 terms dictated by this sigma notation. Okay, so we've got the terms all written out. And then to find the sum, you would just add up those actual values. So you'd take 1 plus 8 plus 27 plus 64. And this happens to turn out pretty nice, actually. These 3 terms together just make 36 plus 64 gives us a nice even 100 for the answer there. All right, so there's our first sigma notation. And then the next one gets a little bit more fancy here. We're taking the summation from k equals 2 to 4 of -1 to the k over k. So notice how we do have a different starting index here. K equals 2 instead of 1 this time. We are still going to end at k equals 4. That's just a coincidence. There's nothing special about the number 4 for a finishing index. And then our formula is a little bit more interesting here. Let's see. So take your first k value, k equals 2. We'll write down that term, -1 squared over 2. And then bump your index up to k equals 3, -1 to the 3rd over 3. And bump it up again, add your next term, -1 to the 4th over 4. And then we notice that, hey, that's our stopping index. So we get to stop there at k equals 4. And so we've just got 3 terms in this notation here, this summation. So now we'll find the actual values and add them up. That would be 1/2, and then our next term would actually be negative. Since it's -1 to the 3rd, we'd have -1/3, and then plus again 1/4. So that is kind of an interesting feature of the sigma notation summations here, is that even though it is a summation, a sum or adding up different terms, you can still incorporate subtraction in here. If you have like a negative number to some power. So you can work subtraction into these. This is actually called an alternating sum here. Okay, so if you want that plus minus feature, your formula is usually going to have something like -1 to the k power, or -1 to the k plus 1, something along those lines. Yeah, or you could put in like any negative number inside of there. It doesn't have to be 1. You could do like -3 to the k, or -5 to the k plus 1. Those would also alternate. So yeah, if you need an alternating sum, you'll incorporate something like that in your formula. Now let's see, to add these up, just to kind of finish this one off here, you'd get common denominator for everything. 6/12 minus 4/12 plus 3/12, and we'd get 5/12 for that summation. Nothing too special about these, like actual summation answers here. Most of what we're doing is just seeing what these things look like. Okay, let's see. So far, so good. Looks like it. Nothing in the chat there. All right. So next thing we'll look at here is expressing a sum using sigma notation. So this is going the other way with things. And we're going to start with the terms and work our way back to the sigma notation. So for the first one here, you've got 2 plus 4 plus 6 plus 8 plus 10 plus 12. So you can kind of see a little bit of a pattern forming there, hopefully. We've got to work that pattern into a sigma notation. So you'll want to see what starting index you want to work with. And, you'll kind of work along with this example as we're going through it here. So decide what index you want to start with. It might vary, but I'm going to go with the classic k equals 1 here. And so then each term is just going to increase that index by 1. So there's k equals 2, k equals 3, k equals 4. Sometimes writing these out can help you spot the pattern if you're not getting it right off the bat. And actually writing out those different values of k gives you quite a bit of information for your summation here. We said we're going to start at k equals 1, and then I can see that it's going to stop at k equals 6. So we're going from k equals 1 to 6. All we need is the formula for our terms there. So for those of you on the call here, what do you think our formula is going to be for these terms? Let's see if anyone gets it in the chat here. Pause the recording for a sec. All right, so we got two different answers. Yeah, we got k plus 2 and 2k. And yeah, now the person who had said k plus 2 is like, I think 2k works. So yeah, 2k is going to be our formula here. So 2k, but k plus 2 was not a bad guess to start with. You can always guess at the formula and then just double check it for the rest of the terms. So like k plus 2, if we took that formula for even just the first value there, taking k equals 1 and adding 2, that wouldn't actually give us the first term that we want. It does work out all right on our second term, 2 plus 2. But yeah, it didn't work out for all of the terms, like not even the first term there. So we get to, yeah, kind of discount that formula. Yeah, in the chat there, K plus 2 was my first guess too, but then I saw it didn't work for the last few. So yeah, true. So that's kind of how we just work through these things. You make a guess and see if that works for all the terms. So yeah, here is our sigma notation for these. K equals 1 to 6, and our formula turned out to be 2K. All right. So for the next one here, let's think about this one. We've got a little more complicated, 1/5 plus 3/5 plus 1 plus 7/5 plus 9/5. So let's kind of start out in the same way here. What do you guys want to make our starting index? Do you want to stick with K equals 1 or switch it up? Any preference? Looks like no preference so far. Oh, 1/5. So while that's not a bad idea, the index K does actually need to be an integer, whole number. So yeah, we can't start with 1/5, even though that might be nice. So let's go with the classic then. Let's do like, oh, there's an idea. K equals -2. Interesting. I think I'll start with K equals 1 here, but yeah, we'll also look at some of these other ones. There is a question in the chat, would 0 count as an integer? And yes, that would count as an acceptable starting index there. So we could go K equals 0. Actually, let's do it a couple different ways. So I'll start with K equals 1, and then we'll also look at your other two ideas there, -2 and 0. So that's one of the things to know about these sigma notations, is that you can actually write a different sigma notation that will give you the same sum of terms. You can do different sigmas that will still give you these same 5 terms being added up. It's kind of interesting. It's almost like a little bit of a puzzle, and there are multiple answers for how the puzzle can be put together. So like this would be kind of my approach here, starting with classic K equals 1, and I would go K equals 1 to 5 with this. Kind of noticing here, we have this random integer 1 in the middle of the whole thing. I would rewrite that in kind of a form that looks more like the other terms and say that's 5/5 instead of calling it 1, because everything else is like a fraction over 5. So let's write that 1 as 5/5. Because then it kind of makes the pattern a little more clear here. Everything's going to have a denominator of 5. And then on the top are all odd numbers in this case. So let's see, there's a nice way, or a couple ways, to express odd numbers in sigma notation. So note here that we had, in that previous example, we had a sum of all even numbers, and our formula was 2K. So that's kind of worth noting there. Even numbers. A nice reliable way to get a formula for even numbers is to do 2 times K, because 2 times anything will always turn out even. So even numbers, 2K. So what do we think about odd numbers? There's a nice way to do a formula for those as well. Any ideas? Yeah, there we go. 2k plus 1. Good. Yeah, so 2k plus 1, because if you take an even number, 2k, and add 1 to it, the next number is going to be odd. So that's great. 2k plus 1 will give you odd numbers. You could also do 2k minus 1. It's a very similar idea. Take an even number and subtract 1 off of it. That'll bring you to an odd number as well. So yeah, these are some good kind of basics to know there for sigma notation. So our formula could be something like 2k plus 1 over 5 or 2k minus 1 over 5. I guess before I put that in, we need to see what's going to work for our k values that I've chosen here, since we set our starting index to be at k equals 1. Yeah, 2k plus 1 here would be, 2 plus 1, that would be 3. So yeah, there we go in the chat there. 2k minus 1 is what we're going to want. 2k minus 1. Cool. All right. So yeah, because of the way that starting index was set, we'll go with the 2k minus 1 option for the odd numbers. Okay. So yeah, that's a good one. Let's see. We want to also play around with those other starting indexes that you guys mentioned here. One of them was k equals 0. Okay. So k equals 0. Then we'd go to 1. K equals 2, 3, and 4. Okay, so we could also write this as k equals 0 to 4, still keeping 5 as our denominator, but then what would the numerator be? So we still want those odd numbers. Oh, okay, yeah. So the person who was thinking about using 0, she says it wouldn't work for yours, probably because of the way you're setting the numerator. So if you change that starting index, you can still make the formula work. You're just going to have to tinker with the other parts of the formula as well. So we can't keep the same 2k plus 1 on, or sorry, oops, I gave away a spoiler there. We can't keep 2k minus 1 on top for this. But for the odd numbers, in this case, if you're starting with k equals 0, you can actually use 2k plus 1 now. Yeah, good. Got that in the chat there. Nice. So 2 times 0 plus 1. Yeah, that'll give us the right odd numbers that we want. So yeah, we can use 2k plus 1 if you're starting at k equals 0. You'd use 2k minus 1 if you're starting at k equals 1. Yeah. Cool. So yeah, 2 different answers so far that would both give us the same terms. Let's also just kind of check the last term on this one as well, just to make sure. 2 times 4 plus 1. Okay, that would be 9 over 5. Okay, good. 9/5. Yeah. If you check through the ones in the middle as well, it works out. So yeah, you could have either one of these. Or someone had also mentioned an index, starting index of k equals -2. Do you guys want to look at that one as well? So I think we could work that in. Yeah, okay, let's do it. So if you start with k equals -2, then you go -1, 0, 1, and 2. Okay, that gives us the basic sigma setup here. K equals -2 to +2. We still want the 5 in our denominator. And now let's think about the numerator for this one. This one might take me a little while too to think about, since it's one that I haven't personally done so far yet. But yeah, we just want to think about how to get that pattern of odd numbers from these k values, 1, 3, 5, 7, and 9. So let's see. If you guys come up with anything in the chat, let me know. I might pause this for a second while we think about it. All right, so yeah, we came up with the numerator here. Turns out we need to use 2k plus 5, and this is actually pretty cool. Plugging in all of these different k values for 2k plus 5 is going to give you the nice pattern of odd numbers that we wanted, the 1, 3, 5, 7, and 9. So yeah, this is really neat. A whole new option for the sigma notation here. So there's 3 different forms for this second example so far. All right. Yeah, that's really cool. Let's see, there's one more that I actually wanted to highlight for you guys. They just keep coming. What if we thought about factoring out 1/5 from all of those terms, since in all 3 of the formulas we have so far, everything's like just over 5. So what if we did like 1/5 and then our odd numbers? 1 plus 3, whoops, plus 5, plus 7, plus 9. That would actually be the same summation. Right? Because if you redistribute, everything would look okay. But that gives us another way to write this. You could actually pull the 1/5 out of your sigma entirely and just do 1/5 times a summation of those odd numbers. Since that's most of what we had to focus on in making our formulas here, it was like, okay, what's the numerator going to be in each case? You could take any of those numerators and put them in like this. So if you went with the k equals 1 to 5, you could just put 2k minus 1 while taking the 1/5 out. Or you could do like your k equals -2 to 2 and put in your 2k plus 5. So there are a lot of different options here for how we could express that second example. It's kind of crazy how many options there are. So yeah, pretty interesting.